Okay, let's talk about the relationship between the second derivative and the concavity. Remember that we say that a graph section is concave up when it looks like part of a smile. So this whole graph right here is concave up. Any part of the graph we're looking at is concave up because it's part of a smile. Now, what does that have to do with the second derivative? Well, it has to do with rates of change. If I have a function whose rate of change is never changing at all, it's a line. If it bends at all, it's got to be concave up for a section or concave down for a section, and let's see which. When I start moving this point along the graph from left to right, I can see the slope goes from negative to much less negative to much less negative to 0 to a little bit positive to more positive to more positive. Remember, that's not the same thing as saying the derivative is negative or positive. Right? Way to the left, the derivative is negative. Way to the right, the derivative is positive, but the derivative is increasing the whole time. It's increasing here, it's increasing here. Now, what does that have to do with the second derivative? Let's go. So we see from the graph that if the graph is concave up, the derivative increases. And here we use an important fact. We know that when any function increases, its derivative must be positive, and that applies to the first derivative as well. So when the first derivative is increasing, its derivative, the second derivative, must be positive. Let's put those three things together. When the graph is concave up, that's the same thing as saying the derivative is increasing. That's the same thing as saying the second derivative must be positive. And as a final note, note that when it's concave up, the tangent line is always below the graph. Talk about concave down. It's going to be very similar. Here I have a graph is concave down. Remember that a graph is concave down when it looks like part of a frown. Right, so any part of this graph is concave down because any part of this graph is part of this frown. If I start moving the point on the graph from left to right, you can see I have a very positive slope, much less positive, 0, a little bit negative, more negative, more negative, more negative. Right? Now that's not the same thing as saying the derivative is positive or negative. Over here, the derivative is positive. Over here, the derivative is negative, but it's decreasing the whole time. So the concavity is not about whether the derivative is positive or negative. The function is concave down when the derivative, the slope of the tangent line, is decreasing. Let's put those two things together. Yes, the graph is concave down when the derivative is decreasing. And now we're going to use the same thing as we said before. We know that for any function, when the function decreases, its derivative must be negative, and that applies to the first derivative as well. In other words, right here, if the derivative is decreasing, its derivative, the second derivative must be negative. And I'm going to put those three things together. When the graph is concave down, the derivative is decreasing. That's the same thing as saying the second derivative is negative. So we get our conclusion here. And one more thing, if the graph is concave down, the tangent line is always above the graph. That's used just as much as the other three facts. Now here's a little summary page saying exactly what we said. Remember that the function value is always about height. When f of x is bigger than 0, the graph is high. When f of x is less than 0, the graph is low. F prime of x, the derivative, is always about going up or going down. So when the derivative is positive, the graph is going up. When the derivative is negative, the graph is going down. The second derivative is about concavity. So when the second derivative is positive, the graph is concave up. When the second derivative is negative, the graph is concave down. And I want to take one more look and just look at kind of a wiggly graph. This is a polynomial. You can see the equation there. And all I want to do is pick a couple points. I guess I'm going to lower it a little bit. Hold on a second. Let's do that. And move up the graph like this so I can actually say something. Okay, here we go. Now, look at the point I have. At the point I have, right, the point is below the graph, is below the x-axis, so the function value is negative. It's going down, so the first derivative is negative, but it's part of a concave up piece, so the second derivative is positive. If I go to here, say, right there, yeah, what do I have? The y value is negative because I'm below the x-axis. The derivative value is positive because I'm going up at that point. Now, this is a funny point because do I think the second derivative is positive or negative here? Well, this is part of a very straight part piece. It's not frowning up. It's not smiling up. It's not frowning down. So I would actually say the second derivative is 0 there. Let's go to another interesting point. See, how about right there? Right there, the function value is 0 because the height is 0. The first derivative value there is 0 because the graph is not going up or going down at that point. The second derivative value there is 0 because it's not opening up or opening down at that point. Finally, let's just go to, say, here. What can I say about that? The function value there is positive because it's up above the x-axis. The first derivative value is 0 because it's not going up, it's not going down. So the first derivative there is 0. The second derivative is negative because it's opening down at that point. So summary there, the function value is positive, the first derivative value is 0, the second derivative value is negative. And we'll see a lot of problems where we have to evaluate this kind of thing.